Good afternoon, everybody. It is my pleasure to welcome Dr. Zheng as a WIN seminar speaker this afternoon. He is a professor of medical biophysics, biomedical engineering, and pharmaceutical sciences at U of T, a senior scientist in the Joey and Toby Tannenbaum Brazilian Ball Chair in prostate cancer research at the Princess Margaret Cancer Center.
Doesn't mean I can dance, no.
You can do lots of stuff. Brazilian ball.
That was really a dance competition.
Oh, yeah? Awesome. Zheng received his PhD in 1999 from sunny Buffalo in medicinal chemistry. Following postdoctoral training in photodynamic therapy at the Roswell Park Cancer Institute, he joined the University of Pennsylvania in 2001 as assistant professor of radiology. Since moving to Canada in 2006, his research has been focused on developing clinically translatable technologies to combat cancer. His lab discovered Porphysome nanotechnology that opened new frontiers in cancer imaging and therapy, which was named one of the top 10 cancer breakthroughs of 2011 by the Canadian Cancer Society. Awesome. Dr. Zheng is an associate editor of the Bioconjugate Chemistry and a fellow of the American Institute of Medical and Biological Engineering. Please welcome with me Dr. Zheng. The seminar is entitled Porphysome Nanotechnology Discovery, Clinical Translation, and Beyond. All yours.
Thank you. Thank you very much. This is, I think last time I was here was 7 years ago. I was giving a seminar in the Department of Physics and Astronomy. And so this is a quite different audience and a quite different, everything I've been talking about today was starting 5 years ago. So I just want to give you a journey of discovery of nanotechnology and how we, from the chemistry point of view, how we design, how we think, and how we actually to making this one all the way try to making to the clinical translation. So let's talk about nanotechnology. Cancer nanomedicine has generated tremendous amount of promise. Maybe I can say hype because of so much promise in putting in. The idea is the nanoparticle, you can put in so many agents into one particle, right? Just like a Lego, you have different function block, you put in together, different function bring together, generating so much multifunctionals. And that's because of that, we have huge amount of investment. In NIH, NCI alone, Cancer Nanotechnology Alliance Program, so far, 10 years, $4 billion. There is a lot more investment everywhere else in terms of beyond the cancer. But this really gives a sense on how this scope is actually developing. But one big thing, especially for the last year or two, people starting to realize why so many papers, there's so few drugs. Right? There must be something wrong with this thing. Why all this promise has not been realized? So there are different, kind of reflection on different in the field now. People think about how the nanoparticle, how difficult to get into the tumor, and there is different kind of thinking. But one of the things, in my view, is a very important limitation. It is the very nature the nanoparticle does best, that is bring multifunctional together, is also generally the biggest hurdle for cancer nanomedicine because you have a complexity involved. When you're talking about FDA, Health Canada, if you're talking about 2 elements, they're already starting to say, wait a minute, it's complicated. If you're talking about 3 elements, like the hell break loose, there's no chance for them to get into the patient. So it's actually pushing us to think about the other way around. That is, instead of this all-in-one nanoparticle, what if we think about one for all? Think about if you're starting to, instead of building from different break, which has different function, what if we self-assemble from one function block, has a multiple function? Now you're giving them a plus in nanoscale property, and this will generating a very simple kind of form with multiple functions, right? So single element things. But difficulty is where you find these multifunctional building blocks. right? So one of the things in nature, obviously, is the gold nanoparticle. The gold has, you can do the electron density, you can do the CT, you can do the photonic property, So gold is very good, but organic-wise, you won't have many function blocks can do more things. The one exception is in nature. That was porphyrin. We know what porphyrin, everybody knows what porphyrin is because porphyrin is everywhere. It's a color of life. If you have a magnesium porphyrin that was in the chlorophyll where the photosynthesis happened, right? So converting the cyanide, carbon dioxide, and water to the oxygen and glucose, basically giving the people the oxygen to breathe, give us the food to eat. But what's in your body? That's hemoglobin. That's iron porphyrin. So obviously, without iron porphyrin, the heme, without the chlorophyll, they won't have a life. But not only the color of life, porphyrin is also well used in the biomedical application, particularly in the area of photodynamic therapy and the fluorescence imaging. In the photodynamic therapy, the porphyrin interact with light and oxygen, generate cytotoxic single oxygen species, leading to the cancer cell kill, but porphyrin by itself is a fluorescent dye. That's why in Europe, they already proved for the porphyrin, for the fluorescence-guided surgical resection for brain tumor, is already approved. So one thing people didn't realize is, actually we started trying to think about is, what if I replacing the manganese of the chlorophyll or the iron in the hemoglobin? Replace that with a radioisotope, like copper-64. Now you have a chance to transform a photonic material into a nuclear medicine material. So we thought we made a beautiful discovery until we realized German did it 60 years ago. In science paper, nevertheless, right? In the 1951, they already showed the copper-60 porphyrin using for the tumor localization. In 1957, they're already using 23 patients, way before the PET imaging is even discovered. That's why people forget about this because it doesn't go anywhere, because there's no instrument, no PET, right? So a lesson here is, if you think you discover something, look back. If you don't find anything, look even older. But the bottom line is the porphyrin is really a beautiful multifunctional building block. So let's look a little bit deeper on what's the photodynamic therapy concept. So in the photodynamic therapy, you have light, you have oxygen, and you have the porphyrin photosynthesizers. Any of these elements missing, nothing to work. So that gives you different way to control the selectivity. So one way to control is control how the light is delivered, right? So in that case, for example, in our lab, in our physics group, we actually can help to using the fiber. Nowadays, fiber can deliver the light to anywhere you want them to be. So you can deliver the fiber directly to the tumors, or chemists can design new way to targeting nano agent to make the agent more selective to the tumors. Or you can control, as our concept called photodynamic molecular beacon, essentially because it's a process to generate single oxygen. If we silence this process, then there will be no longer possible for the killing until you have cancer signatures trigger this activation. So that's our concept called activatable photosynthesizers or the photodynamic molecular beacons. So after this concept was introduced, now after many years followed, there is many people in the world, different research group, develop so many different kind of activation strategy. There is enzyme activation, nucleic acid strategy, and a self-quenching different kind of way. So a couple of years ago, I think 2009 in the summer, my student John Laval, who is actually system design major from Waterloo, as undergraduate major, doing the softwares. He came to me, he said, I want to do a nano beacon. Basically, he wants to make an activatable agent based on nanoparticles. The idea is very simple. If you put all these porphyrin molecules together, they will be quenched, right? Packing in a nanoparticle. If you dissociate, it will be activated. So it's a very simple idea. Then I say, if you want to do it with a clinical formulation. That with this porphyrin, if we're doing this visual dyeing, for example, this is a 1% porphyrin loading in the liposome bilayer structures. So do this way. Then we found out, obviously, when you're adding about 5% porphyrin, this structure gets broken up because the porphyrin is a bulky molecule. In the bilayer of too many, they just doesn't work anymore. So the idea is, what if we replacing one of the fatty acid chain with a porphyrin? Now you have a porphyrin-lipid they should be more closely mimicking the lipid. So the idea is you titrating this one into this lipid, you will have a better chance of the porphyrin loading in the liposome. So surprisingly, my summer student that time, Elizabeth, now she's graduated as a PhD in the Harvard Medical School as a resident. If you look at what she did, she found that the more you actually load this porphyrin lipid into the lipid, the more quenching, obviously, you get. But the more important is the particle become getting more stable. Totally opposite than what we're thinking. I said, how is it possible? In the end, get 100%. That means every single lipid is disappeared. It is really a self-assemble of this porphyrin lipid structure. And the only way this porphyrin lipid structure can exist is, we demonstrate, is this TM structure, is in the bilayer structure. Because porphyrin is a hydrophobic. So the only possible is hydrophobic 2 rings in the middle, polar has sticked out. That's a liposome structure. Only when I see this structure, then I suddenly realize this structure is possible. Because now you think about it. When your porphyrin is disrupt each other, but the porphyrin can aggregate. The aggregation property of the porphyrin becomes stabilization force for their self-assemble. That's why the more you add this porphyrin lipid, the better actually they become more stable. So that was totally shocking to us at that time. Now everything makes sense. So if you look at this cartoon structure, bilayer structures, right? Now we're talking about how many porphyrin? About 100,000 porphyrin. Each of them are light absorber. So that means instantly the extinction coefficient is in the gold nanoparticle range, right? So that's why you can do photothermal. So we show you can do the photothermal therapy in the original paper. You give the IV injection of the nanoparticle, accumulate in the tumor, shine the light. This is not fluorescence, it's an infrared camera, basically showing the temperature increase. So 60 seconds, you can see a temperature increase 30 degrees. You actually can destroy the tumor completely. The same photothermal conversion process is very good is actually the, before I go there. So if the particle, so the question is, once the particle dissociates, you have a photodynamic therapy effect because you restore the monomers. So the question, the reviewer came back saying, how do you know the process killing the tumor is purely photothermal, not photodynamic? To answer this question, my student Chen came up with this idea. He said, photothermal is about heat. It's purely a physics property. Photodynamics is about the single oxygen, so it's a chemical process. If I take out the oxygen, then it shouldn't work. So she actually said, we do this experiment. Then she created this model. You can have the 2 tumors, one side is the same thing. You have one side making them hypoxic, which is a mix of oxygen with oxygen, the other side with the oxygen. Now you do the treatment. We confirmed that by the HIF-1 alpha, also based on the photoacoustic imaging. We showed there was 2 differences. Then we design an experiment. If exactly the same drug concentration, same porphyrin, exactly the same light dose, the only difference is power. In the low power, favor the photodynamic. In the high power, favor the thermal process. Then we show in the Porphysome case, right, in the both oxygen with oxygen, temperature both increase. So we know the thermal works. Now what you show is when you have the Porphysome, you destroy the tumors. But if you're in the lower power, nothing works. In the traditional PDT aging, this is the clinically approved photophyrin, only works with oxygen. Without oxygen, it doesn't work. So we know it is truly because of thermal effect, and we demonstrate it works with survival and things. So now the question is, we know when the nanostructure is a photothermal. We also know the monomer is photodynamic. So how do you know at which time is how much percentage is actually is intact, how much percentage is actually monomers? Because the intact one is no fluorescence because everything's quenched, remember. So my student came up with this idea, say, what if I give them the fluorescence? Make a dark porphysome become fluorescent. So in this case, he introducing the energy transfer, introducing another dye, another porphyrin, and basically only happen, which is when it's intact, when it's dissociated, this energy transfer disappear. This give you about 100 nanometer, almost like a Stokes shift, artificial Stokes shift. With that, he was able to make a porphysome like quantum dot. Inject, you will see there's a bright fluorescence without changing of the thermal conversion. So now we have a way to tell dynamically how much percentage is intact, how much percentage is actually dissociated. So use that by using the ratio metric. Porphysome was completely dark. By using this flat porphysome, we can actually using the ratio to define how much percentage is there. So another thermal conversion property is a photoacoustic. Because unlike photothermal, you hit a continuous sign laser, absorb the light, it generates heat. If you give the pulse laser, now what you have is you have the transit temperature increase, lead to the thermal expansion of the elastic expansion that generate acoustic wave to detect by the ultrasound. Photoacoustic is a light-in acoustic wave sounds out. The idea is now you have much, much high resolution because photonic is scattering. So it's very, you can go pretty deep, but it's very light, very scattered. But you have lights in, you have acoustic out. Now you have very, very high resolution. So that's the idea. So with that, we demonstrate, because such a high thermal conversion, we can have very nice in the lymph node, in the lymph vessel, everything shows up. And you probably already know why without porphysome, the vessel is very nice and photoacoustic. That's because hemoglobin is also porphyrin, right? So it's blood vessels. So I mentioned what we want to do now is what if I want to, original concept is a nanobeacon. And we still can do that, especially if you introduce the targeting. If I put a targeting, the particle will be disrupt inside the cancer cell right away. It will lead to the activatable fluorescence and PDT. So that will give us eventually what we originally designed for purpose of porphysome is for activatable agent. So we can do the low background fluorescence and a very strong photodynamic. So as I mentioned, we know how to inject radiolabel isotope, put in the porphyrin, right? But we were very lucky to find out TD is also a Waterloo student. So we find out he's at MIT right now doing the PhD. So we find out if you have a preformed nanoparticles, right? The porphyrin, each of the porphyrin can easily label 100% of this copper 64. All we need is 0.1% radiolabeling because PET imaging is very sensitive, right? So that means now we have a way to real-time tracking where they go. We don't need another chelator to tell you what happened to this nanoparticle. Now our building block of the nanoparticle itself is a chelator. So you can track them where they go. You can do the PET imaging with that. We show it works with very nicely with this orthotopic prostate model. You can see the PET imaging. Fluorescence, you can see as well, but you have to open it up, do the surgery. You can see the tumor right here, but in the PET, you can see the in vivo. And what's the most interesting part of this study is same model with the two modality. We get exactly the same ratio from the tumor to prostate with this both gamma counting and the fluorescence. So that means what you see is really what you get, right? So with this, we can use it for different kind of PET imaging. We show in this case, you can have we created this model for the bone metastasis model. You can see this is the very nice, tiny bone mats can be shown up by this imaging, and it's about 1.65 millimeters. So the PET resolution, micro-PET resolution is 1.47 millimeters. So we really are good to all the way to the resolution limit, can pick up the very tiny nodule in the tumors. So TD also came up and saying, we did this with a very tiny labelable percentage because PET was so sensitive. Imagine if I labeled, we actually label up to 30, 40%. That becomes very hot enough to be generating the radiotoxicity, can be a radiotherapy agent. But what if I introducing every single porphyrin with a paramagnetic metal, like manganese? Now all of a sudden, you have a chance to overcome the MI sensitivity issue. Because MI is very, very low sensitivity. What if what we're thinking here is nothing, is pretty trivial. It is the sheer number make a difference. If you time 100,000, now you have a very, very strong MI sensitivity. So that's the idea. Not only that, if we label with manganese 52, now you can do the PET, right? So basically what you have is MI, PET, and still optically absorbing, so you still have still have the photothermal and the photoacoustic. And basically that's really the introduction of the porphysome concept. That is, you have one molecule, less than 1,000 molecule weight, self-assemble into a nanostructure to capable of all these functions. So that's the essence of the non-Lego concept of the porphysome. So the advantage of that is not only you will have chance to lower the development cost in terms of future development in clinical translation, because you develop one, you actually can apply for different things. More importantly, we can custom-made, tailor-made different functions for each different clinical applications, because we don't need it for all of them for one particular application. So that's a summary of last 4 years. We have validated the Porphysome multimodal theranostic utilities in different kind of species. We did a mouse, rat, hamster, rabbits. We are now finally have our very first dog prostate tumor model. And we did it with the different tumor types, orthotopic, primary, right, metastasis, carcinogen-induced. And we have done all different cancer types, pancreas, ovarian, brain, you name it. This is here just basically show a few examples. We did all of them. So I'm going to show you, switched gear to really tell you a little bit about clinical translation, how we actually can design nanoparticle for clinical translation. The first criteria is you have to matching the unmet preclinical need with the Porphysome utilities, nanoparticle utility. If you think I can using every single function for one particular application, you have no chance. If you can find the minimum application utility for each application, that's really the way to go. Not the maximum, but the minimum. In some case, one function is all you need. In some case, maybe two functions is needed. But they have to match in a clinical utility. Give you two examples. One, focal therapy of prostate cancer. In the Princess Margaret in my hospital, we have this agent-free photothermal ablation for focal therapy. That is, put the patient in the MRI magnet. Now you have planning for where you insert the fiber very precisely, shine the light. Now you're monitoring by MRI, temperature thermometry, MRI thermometry. With the temperature raising to about 55 degrees, that's where the photothermal coagulation happens. There will be tumor reaching the point of no return. You stop the treatment, you follow MRI, you see the tumor's gone. So following this particular MRI guidance, we don't need anything else. So we did orthotopic prostate tumor model, follow the clinical protocol, put an MRI. Under the MRI, we insert the fiber. You can see this fiber right here, insert to the tumor. Now you follow fired up the laser. You see the temperature increase by the MRI thermometry. As soon as it reaches the temperature, you start the treatment. Now you see a beautiful change in terms of response. On the MRI, we see there's nothing. The tumor's gone completely, and the control, it keep growing. So selectivity is very good. If you look at only the tumor got destroyed, the most important for the prostate cancer is maintain the rectal wall. Because the rectal wall, if you damage the rectal wall, you basically have a lot of issue. So the rectal wall is normal to completely reserved. So the question is why is it so selective? The nanoparticle must have some tumor selectivity. And how do we know that? Well, we have a PET imaging, we have a fluorescence imaging, so we can study it. Indeed, by taking advantage of the PET imaging, we can see the tumor to all the normal tissue, the rectum, the prostate, the testis, and the vesicle, all have very high selectivities. Inject dose per gram is about 4.36, is very good, and fluorescence showing exactly the same thing as tumor. So the reason we don't want to get into the reason why the porphysome accumulate in the tumor so nicely, but the fact is we got very high selectivity, allow us to differentiate tumor and from the normal surrounding tissue, generate a very nice therapeutic index to lead to the thermal response. Now I give you another example. In this case, we really need not just one function, we need two functions. This is a lung cancer model, and we're doing this lung in the peripheral lesion. So the lung is actually bronchial going to different branch. If the tumor is in the central lesion, it's very easy. You can get a light there, you can destroy it. What if the tumor is in the peripheral lesion, and they're away just next to the bronchial, essentially behind the bronchial wall? What do you do, right? In this case, right now there is, especially in this patient, which is difficult to do the operation. There's many of them, right? The lung function is not working very well. You cannot do the surgery. So in this case, we want to do the idea is, what if we using the bronchoscope? And the bronchoscope can feed all the fibers. You can do the detection, you can do the treatment. If we can use the bronchoscope to find the tumor behind the wall, Then I can stick the fiber to ablate it. But the bottom line, you have to find the tumor behind the wall, right? So what we show is, first of all, we're creating this model, lung isotopic model in the rabbit. Why we do rabbit? Because rabbit is about 4 kilograms. It's like a baby. So the pediatric bronchoscope is the smallest bronchoscope, is the pediatric bronchoscope, can go to about the same size as a rabbit. And when we use that, we're actually showing the first time we get a tumor there. We confirm the tumor is actually encroaching around the bronchial wall. We confirm the porphysome accumulation is there. Then, collaboration with the photonic group, we designed this new bronchoscope with all the thermal ablation ability. We see the fluorescence of the 45 minutes after injection of the porphysome deep in the lung. You see nothing. But 48 hours later, when the porphysome started activating, you'll see 1 and 2. If you tune in your eye, you can see the tumors popping up. These are not like a colon. Colons, the tumors pop up on the surface. You can see them. You can spray it, you can see them. These are the behind the wall. It's on the flat surface, but you can see them. And that is very important because you see this breathing very fast. Rabbit is breathing so much faster than human. And because of that, if you don't see the tumor, how can you ablate it? That's where the imaging guidance is absolutely critical. With this, we were able to show it works, and we can see the big difference between the porphysome photothermal versus the regular one. So again, tell you that really the matching this need is very important. The second is, if you want to push in translation, there is other small details to be considered. And these are things which academics normally don't talk about. Huge problem. IP, toxicity, scale up, GMP, many, many things. So we were very lucky because we were discovered the porphysome, but purely by accident. We didn't expect it. That's actually very good for patents. So we got the patent was issued last year, and the US and China and Japan is all issued. Then we actually we still don't have investment, but we got the patent issued. Then we see the toxicity is important. We inject porphysome in the original paper. We inject 1,000 milligram per kg. Give you a sense, like a mice is 20 tiny, 20 gram, 25 gram. We inject about 60 milligram into about 100-fold, about 1/100th of the whole mouse weight of the material into the body. The ear turned blue, everything turned blue. The mice is healthy. Why is that? Because the porphyrin is made with chlorophyll, right? So it's actually undigested. We demonstrate that we can see it can be digested in the liver and the spleen. Is after about 12 hours, you actually can get the porphyrin-lipid digested, cleaved. Then porphyrin goes their metabolic pathway, lipid go their own metabolic pathway. So that's actually called truly biodegradable. But in the blood, it's intact. That's important because it allows the porphyrin nanoparticle, behavior nanoparticle, go in circulation to go to the tumor where they want. We're also solving the problem of the scale-up synthesis. And I convinced my student, Microbubble, a brilliant graduate student, take on this thankless job to do the GMP and SOP because nobody invested us. We have to do it, so get a student doing it, even though the paper was completed unpublishable, because all he did is 6 months stability, measure the size and everything. Was just did the beautiful GMP kit for the patient use, and this is actually under all the GMP condition and adentoxin free. So this is truly pure interest and desire. He has to do something else for his thesis, otherwise he won't get a graduate. But this is basically just to give a sense on how we are and where we are. We finished the very first pre-CTA meeting with Health Canada this Monday. So I think now we are picking up speed to go a little bit further. So I want to use the rest of talk about what's beyond porphysomes. So the first thing I want to talk about is porphysome is a completely accidental discovery mimicking the liposome structures. Then a lot of people ask me, can you make a porphysome smaller? Certainly, we're not reinventing the wheel. Whatever the liposome can go smaller, we can go that smaller. We cannot go even smaller because high lipid curvature prevents the liposome to become stable when it's a very small size, like 50 nanometer less. However, nature does all these beautiful things. Nature knows how to make a small particle. One of the smallest nanoparticle nature can make is a 5 nanometer to 10 nanometer HDL, high density lipoprotein. For you guys probably didn't know. For the Holger and I probably will know because we're starting thinking about good cholesterol, bad cholesterol, right? Our Frank probably you're too early, young for that. But for the good HDL, which is HDL is about 510. How they did it? Because it's apo-amphiphatic alpha helical bundle. They're almost like rubber band, put the nanoparticle, squeeze the nanoparticle, making it very small. Using the same concept, we made a porphyrin nanodisk about 5-10 nanometer size. We're showing exactly the same structure. More importantly, Sarah and Chalya made something very exciting. We make almost like a mini porphysome. We made a spherical structure with monolayer instead of bilayer, about 20 nanometer size, beautifully shaped. And now what you have is something very interesting. Not just a small size, but also we don't need pagylation anymore. All the nanoparticles need a pagylation because they want to circulate in a long time, then allow them to get into the tumors. But nature doesn't have pagylation. HDL doesn't have pagylation. LDL doesn't have pagylation. They circulate in the blood very long time. How they did it? Don't ask me why, but we're mimicking the natures. We were able to show that they have, with or without pagylation, they have exactly the same pharmacokinetics by distribution, right? Another important thing is the porphysome we find out without targeting, without getting them inside the cells, is very difficult to get completely unquenched because there is so much porphyrin in the voxel. But when you decrease the size, you decrease the amount of porphyrin. In this case, if we have this about size, we have about a couple of hundred of porphyrin molecules. It's much easier to dissociate, much faster to dissociate. So we show we can get compared to porphysome, activation is much faster. That means you favor fluorescence and favor PDT. Using this concept, we actually worked out using this much cleaner for the nanoparticle. Instead of photothermal, we focus on photodynamic, we focus on fluorescence. We still can do PET imaging. You can look at this one. This is probably the best image I ever got. You see the rabbit, you have oral tumor. You see not just see the tumor, you see the entire drainage to the lymph node. And you actually, from the tumor, you can visualize all the way to the metastasis lymph node. And not only we can see that in the PET imaging, we can duplicate that, the same agent with the same injection in the surgery, intraoperatively, in the surgical suite. Now you can see this is the pre-incision when the skin was intact, just take the hair out. Now during the surgery, when you open up, you can see the tumor. After tumor resection, this is surgical bed. But if you look at the going forward deeply, you can find the lymph node. You can not only find the lymph node, you see the lymph node for the first lymph node migrating to the second lymph node. I said, my God, it was basically my surgeon was so happy. He said, now not only I can see the tumor, I can know where the lymph node is, and I can know second lymph node. I just keep digging deep. I can do the surgery with that. So that's why we're very excited about this intraoperative opportunity for this for the clinical translation. But more importantly, what if you're taking out the surgical bed surgery? Then what do? You can use the light to treat it. You can do photodynamic therapy. Because I don't even need another agent to inject it. The agent is already there. So this is not for surgical bed. This is for 2 centimeter tumors. 2 centimeter tumors in there. Ablated with the light on the photodynamic therapy. You can see the completely tumor ablation. At 34 days, the tumor is gone by the CT, by circulating tumor cell. There is no symptom of the tumor disease left. So we know the tumor, this rabbit is completely cured. So that's, we think, is a very covering a pretty good clinical perspective in the functions. So now I'm going to switch to the material mode, right? To think about what's the problem of the porphysome. The biggest problem with porphysome is with so much porphyrin stacking the bilayer, how can I don't see spectrum shift? How can I don't see any phase to the transition temperature? So that means you have a highly density pack, but you may have very disorderly pack. You don't have a highly ordered self-assemble into secondary structures. So how can we solve this problem? Again, we're looking at nature. This is really my favorite place in the world. I've been there four times in the Yellowstone. Why Yellowstone? Not just pretty. Yellowstone has this very nice, very biological rich source. One of them is called cyanobacteria. Cyanobacteria is like chlorophyll for the photosynthesis. Cyanobacteria for the bacteria photosynthesis. What happened is in this cyanobacteria, the light harvest complex formed by the one porphyrin, one single porphyrin. But because of the protein put in a different conformation. When this conformation, they're 850 nanometer. When this conformation, they have 800 nanometer. So that means you have external coupling is called J-aggregation. So the merit is the nature using the protein to using a single chlorophyll can make them a different kind of, the colors. And we can show that this is the nature. This is our porphyrin-lipid. Very similar, right? So what we did is we duplicate that. We actually form these structures in the lipid. Instead of porphyrin self-assemble, 100% porphyrin assemble, now we actually give them 15%, right? So the porphyrin using the lipid as a host to holding this aggregate. Once you have that, then porphyrin, as we designed, is starting to aggregate. And they give you the 75 nanometer redshift associated with secondary structure. And they are fluorescent. So that's nice, because now we can have very long wavelengths. We can do dual fluorescence and can do a photoacoustic. You can do showing this one, and I show you one movie. This is a surgical suite using in the surgery. And you can see this is a lymph node, and this is a tumor, right? This is what the surgeons see in their eyes by the clinical system. You will see once you see that, you can do that very nicely. But more exciting property, in addition to the red shift and the fluorescence property, is the transition temperature, is a phase change. Self-assembly combined with phase change is like gold mine. So I'm going to show you examples. So when you have host lipid has a transition temperature, right? So if I have this aggregate, if I cross this temperature, what will happen is this lipid still maintain, but your porphyrin aggregate become dissociated, right? So what that means is you lost completely the signals, optical signature of that. And this can be tunable and it can be reversible. You can see if we're putting the DNA like a PCI cycles, temperatures up, it's the wavelength, 824, temperature down, 750. No, temperature down, 824, temperatures up, 750. You can keep doing it, recycle it. That's very exciting because if you look at the photoacoustic, it's based on absorption. This is no longer fluorescence, this is absorption. Talking about from at the right temperature, from the 90% to 10% of drop of the signal cost only within 2 degrees. This is, if you look at this one, it's very similar to your pH meter, pH curve, pH papers. So with that, we did it in vivo as well. We show it works for the thermal sensing. This is basically, I want to guide you with 2 colors. The red is your hemoglobin, the blood signal, right? So it should be always red, should be always there without temperature increase or not. The green is your signal, your porphysome signal, J-aggregation signal. By reaching your designated temperature, the set temperature, what you expect to see is this signal will disappear. Will tell you the temperature has reached. So take my word, you will see, if we set about 45 degrees, you will see reaching here, you will see the green vanished. So let me tell you, this is incredibly important because if I do the photothermal therapy, all the laser ablations, all the high field, the ultrasound therapy, thermal therapy, what I need to know is that the clinician doesn't need to tell me which temperature. All they need to know when should I stop, right? This is like a pop-up timer. As soon as it's reaching for the turkey, as soon as it's reaching the temperature, boom, done, I'm done, right? So that's the idea. But more importantly, this activation mechanism can be extended, we think, to different mechanisms. Can be different material even, pH, enzyme, can be hydrogel, polymers, as long as you have one nothing binary code into the phase change associated with optical signal change, that will give you the whole word, right? So the idea is we want to use this to making the photoacoustic as versatile as a fluorescence. But the most exciting part of this J-aggregation, of this phase change combination of self-assembly is the next one. So the holy grail of photothermal therapy is you shine the light, you want a stronger absorber like gold nanoparticle, or the porphysome. Absorb so much light, it will generate temperature quickly. But the problem is, 2 biggest problem. One is, yes, temperature can increase, but the temperature may overheat because there's no way to stop it, right? And 2, would absorb the light doesn't go any further because the light got attenuated. That's what generates the heat. So how can you getting the things to treating a more deeper tumor in a more controlled fashion? That's never solving for any nanoparticles. But the J will solve that. Because now what you would have is a feedback loop, negative feedback loop. As soon as I reach the temperature, it will become optical transparent because wavelength shifted downwards. So it becomes transparent. That means they no longer absorb the light. That means the light will go further to heat up next cycle, right? So that's the idea. So this is basically the paper we just published the last couple of months. We show in the regular nanoparticle without light absorber, you see this is, by the way, taken by a cell phone camera, iPhone camera. All the imaging system we have in the lab couldn't do it. The only thing works is the iPhone camera. All the BlackBerry, all the Google or something. But if you look at this, you can see that this is basically we have videos showing the light going through. Then if we use the nanoparticle gold, or any nanoparticle absorbing the light, you will see the temperature keep increasing, but the light cannot go through the whole lens because they stop. But if we're using our J, you actually can see the temperature never go beyond your designated temperature. The light will actually penetrate through. I'm going to show you a movie. This is cell phone camera moving. This is the control. This is also control. You look at this one, the J porphysome, you will see the light slowly in your eye will go through the entire lens. So I'm going quickly. Right? So literally you can see the light take about 5 minutes to go through the entire glass. This is actually, we're very excited about this because now I think this is the future of photothermal therapy because now you can control how much degree you want heat. You want to control how deeply it can go. You still cannot clear the tissue. The tissue is still absorbing it. But you basically take the absorber's factor away from this process. So the reason I said this is my favorite place is not kidding, because there's a lot of things to be learned from here. You probably, everybody know about this one, right? The great tech story, which is the biggest story of this history. Essentially, the story goes, the guy, discovered this enzyme, the polymerase, basically thermal aqueous, deposited in ATCC, and somebody from the company just buy this from ATCC, and he put into the PCR mechanism, won Nobel Prize, and got out the PCR machine, and everybody else got nothing. So the national park, because of that, everybody has signed waiver to work in the Yellowstone nowadays. But what I'm interested in, another one, not just cyanobacteria, but green sulfur bacteria. Green sulfur bacteria give you all these different colors. Why? Because green sulfur bacteria is the most efficient light harvesting complex in the nature existing. It can go all the way about 100 meters on the seabed, ocean bed, it can absorb the light. How is this possible to be so strong absorber? Because this green sulfur bacteria has the fundamental unit called chromosome. Each of them a nanorod. A self-assembled, this is our TEM structure, is from this one single porphyrin molecule self-assembled together without protein. 250,000 of these porphyrin in one nanorod without protein. I mean, nature is just brilliant. How did it happen? I have no idea. The porphyrin molecule self-assemble in the ordered form and lead to the beautiful shift. So if we want to do this, we want to learn from this process, mimicking in our situation. So we actually did a very first step. We show this alpha helical spiral can be formed. This is Sarah did this work. We're showing that actually can see this shift. And using this method, we can do the third harmonic generation, because third harmonic is not existing in the cell by themselves. But you can, because of the third harmonic associated with only this nanoparticle, you can follow what happened to this nanoparticle cellularly. If they disappear, that means they actually becomes, this nanoparticle becomes destroyed. Another thing we want to learn is truly we want to mimicking this nanoparticle in the chromosome sense. We find out in the many literatures, they're already doing this called temporally induced aggregation. They are the chemically induced aggregation based on this kind of structure. You can see this coordination from this metal with this hydrogen bond, then with carbonyl, the hydrogen bond. Essentially, the central coordination metal with 3' oxygen are the key. These people are using this for the chromosome model. What we learned is we actually can do this into the biological sense. We made a porphysome with this method. We show the shift. We demonstrate the structure. We actually works in vivo. We can show that beautifully for the thermal transition. So my final two examples are what else, beyond the porphysomes. We already talked about pretty much everything, all the imaging. The two missing imaging modality I haven't touched about, ultrasound, CT. CT, my student, still a long way to go to get it done because CT, there is no cheating. CT is about electron density. Either you have it or don't have it. Really, if you get a number up, you're okay. But ultrasound, what about ultrasound? Well, this became her main project after she came back from the summer student, become my graduate student. She said, I want to make a bubble, porphyrin microbubble. Very simple. Put this porphyrin-lipid in the gas bubble. Now you have ultrasound. This is for fun. At that time, it's for fun. She even named it Porsche, porphyrin shell microbubble. So I think she liked Porsche. So what happened is afterwards, that was purely just for fun. Then we actually start thinking about how I can use this for. What she introduced now is putting aggregation. If I have this aggregated secondary structure, self-assembly structure, now I have a two kind of optical signature. Ultrasound signature existing when the bubble is intact. When the bubble bursted, ultrasound signal will disappear. But if the bubble bursted, what happened to the bubble? Nobody has this knowledge. In the literature, people are using this microbubble for gene delivery, for all this delivery, through the blood-brain barrier for all this endothelial junction, because the purpose, when the bursting this bubble, the force will bring open the transit opening of the endothelial junction. So very powerful technique in the clinical trial or in the clinical case. But the problem is nobody can design better because nobody knows what happened to them. What we have are the two signatures, either aggregate or non-aggregate. Aggregate gives you only secondary structure, only this thing in the nanostructures, or the non-aggregate means that everything breaks down to the pieces. So use this way, let's find out. Microbubble actually turn to the nanoparticle after ultrasound-induced bursting. That is very exciting because now we preserve that because we have optical readout. For the first time, we can find out what happened to this microbubble. Eventually, look at this one. This is without a conversion ultrasound, microbubble probably about 30 minutes, right? So 2 minutes, sorry, 2 minutes after a while, protein will take them away. Obviously, as soon as you apply the conversion ultrasound, the bubble instantly all bursted. But in this case, we IV injecting the microbubble, instead of waiting for 24 hours, let them go to the praying where they will be, we put in the ultrasound right next to 10 seconds later to the tumor. So now what happened is when the bubble in the circulation, in the tumor, we bursted the bubble. Then the bubble happened is through the endothelial junction, they form the nanoparticle behind the wall. Right? So that's actually really exciting because now we have a chance to truly thinking about new way to deliver the drug. Essentially, instead of waiting for them passively getting the tumor, we actively, on demand, in situ generation the nanoparticle behind the wall that will creating the new area, I think, will be for the nano things. That's why this one get into the Nature Nano because of that. It's not because of the porphyrin, because of the identification of this mechanism may have a chance for the drug delivery. So the final example I'm going to give you, so far I'm talking about everything about porphyrin from the chlorophyll, algae, or the porphyrin from the bacteria, so the bacteria. The one thing we haven't done is all of these porphyrin, they have very small, tiny amount of metal can be chelated into this porphyrin because the pocket is fixed, right? But there is so much porphyrin is in the literature. The one thing we can do is to making a bigger porphyrin. Instead of the full coordination porphyrin, we have a bigger porphyrin called taxophyrin. The reason why I call taxophyrin because of 5 coordination, they're almost like a star. And also Lone Star State is Texas. And this Jonathan Sessler from Texas, that's why he got named his porphyrin called taxophyrin. And I think after that, nobody allowed them to name porphyrin anymore. But that's the last one, the taxophyrin. The beauty of the taxophene is you have about 20% bigger the pocket and have 5 coordinations instead of 4. What that happens is all this metal, about half of the length line, can go very form one-to-one stable. Instead of metal pop up, not stable, useless for the biological application, now you have metal tightly coordinated there. Because of that, you can do so many other things, like nuclear medicine application, radiosensitizers, the whole 9 yards you can really play. So that's basically bring me to the end of my talk. I already show you what can do with the self-assembly of this porphyrin. A single porphyrin-lipid can self-assemble in so many different kind of things. I only can touch touch base about 80% of this possibility. There is a lot more you can do with this. And I'm sure, by no means, this only happens in porphyrin. We call porphysomes because first time we use this porphysome. And we can apply, I'm sure if you can have some kind of interaction between the molecule, you can find all different kind of similar structure, all different kind of property. It's not limited to porphyrin, I can guarantee you that. So my final message, 3 things, very simple. Simplicity is golden. If you ever want to think about clinical translation, you have to think simple. If you start thinking about something fancy, you have 0 chance for clinical translation. 2, clinical need dictate technology. I'm started from the develop some nice technology looking for application. Then we're starting to have to think about different way. From the unmet clinical need, dictate what kind of utility we need. Then the nanostructure can provide to the best matching for that. And the final is my best. Always my learning the best lesson is really nature may not have all the answer, but definitely has most of the time has nice answers. And obviously I have to thank my great group of students. A lot of my first batch of students pretty much all disappeared. And John, TD, and who else? Arash is not here. These are 2 Waterloo product. And there are many other students. And this is the current group. And all this funding. And I have all the, most of the clinicians to thank for because that's my unique location in the cancer hospital. Gave me a chance to work with a lot of clinicians. And thank you. I hope this is useful to you.
Thank you, Gang. Very exciting tour through Porphysome nanotechnology. Questions for Dr. Zheng?
This is a small group, so asking any questions. Yeah, I want to try to give a broad survey of what we have done for the last 5 years, essentially.
So there's what I interested in, one thing you said, aggregation can be G-aggregation to the H-aggregation. So is it a high temperature go to the G-aggregation?
We don't have an H-aggregation. This is a purely J-aggregation. H is more broader, the blue shift. J is characteristic is a red shift and the narrow band and maintain the fluorescence. But most important is J aggregation gave you the astonishing red shift and a very sharp peak. So in our case, 75 nanometer for the J in terms of bacteriophile case. But now we have the chromosome mimicking. We got about 90 nanometer shift and without even have any other structures. So the J is, I think, combination of these aggregation-induced property and the self-assemble phase change are the really very powerful.
So you initial aggregation have no interaction, but peaking have a J-aggregation.
No. Initially, they form the aggregation.
With pi-pi interaction?
Yeah, with edge interaction. Pi-pi is H.
With H interaction.
No, H is pi-pi. So this is basically edge to edge, similar to the nature, like a fence. They are the long wavelengths. But when you heat them to a temperature you set, then these porphyrin aggregate become dissociated. The particles still remain, Is the only thing is these aggregate becomes, you can actually see the color change shift. That's really becomes the color, the absorption change. Now, to me, is like one, probably the best way to think is 1, 0, like a computer language, binary code. If you combine this binary code in the phase change material, now you really can do anything, can do everything. So that's the idea. Question?
Let me ask you about your hexaphorin.
Yeah.
Is that completely flat 5-fold coordination?
Yes.
Can you make that any larger to get flat 6 and 7?
Yes. Actually, no. The coordination, but they actually made a different kind of. But when you get bigger and bigger, the wavelength's getting like even 1,000 nanometers now.
Yeah.
Then it becomes less biological relevant, but for the material sciences become very powerful.
Yeah.
And they actually have all these different haptofrin and all these things. There is a whole big group of porphyrin chemistry world. People are just solely for the fun of making all new molecules.
Yeah, absolutely. But it remains flattish?
Yeah, that's the idea. Is all these big aromatic, aromaticity. Yeah, the taxophrin. He make I think it's a pretty good name, because it looks like a star. It's a 5 coordination. It's like star, and the lone star states. That's a taxophrin, right?
Is that a question?
Just one question here.
Yeah.
For the targeting, right?
Yes.
You said it was actually specific to the tumor. Was it passive targeting? Was it just like, you inject and it just accumulates there, or is there actually an active targeting mechanism?
Yeah, it's a very good question. It's a question I got every single lectures. First of all, we were able to put in the targeting ligands, like EGFR antibody, like folate, we were able to do. But everything I show you here are non-targeted, are passive targeted. As for why these passive targeted can selectively tumor so well, I only have a hypothesis. My hypothesis is first of all, they are like liposome-like, they are nanoparticle-like. Any nanoparticle can go to the tumor to some extent through passive accumulation through EPI effect. What's different, making this porphysome difference, is I kind of sense is almost like you have a way to enrich the porphyrin localization into the tumor area through this EPI effect. Once you actually get into the tumor area, the porphyrin itself has a tumor affinity, because that's why the porphyrin using clinically using a clinical agent, but very low delivery efficiency. But if you have a chance to bring so much porphyrin into the tumor area, then you will almost generate a concentration gradient to help the porphyrin to go to the tumor more easily. So you have a high selectivity versus a liposome-based agent. So that's my hypothesis. People used to be called, when the porphyrin, nobody knows what happened porphyrin to the tumor, people used to say there is a porphyrin receptors. But obviously that's debunked a long time ago. But that's really the idea, is porphyrin has natural affinity to tumor. But if we bring them closer to their home, then it's much easier to get into their house. That's the idea.
So normal cells are not, you don't have that.
No, normal cell is affected. If you have the liver and spleen, you can clearly see tons of this accumulation, right? But that's why we are not keen on using for drug delivery. I mean, we can work on drug very nicely, but I cannot control the drug not go to the tumor, not go to the liver and spleen, right? So that's why we want to combine with a physical therapy, like a light, radiation, X-ray, and try to do this way. Right? So it's not perfect. Any nanoparticle's weakness, it has it. But the idea is you can do something uniquely the other nanoparticle cannot do. So the most important is it offers a potential combination of different function tailored for each application. That's the idea. Yes, please.
So all the porphyrins you showed all have the amino group in there. Have you tried replacing the nitrogen with some other elements like sulfur maybe?
There is all these different kind of porphyrin is actually in the literature, in the community. The reason I didn't do it is because I have a singular focus try to bring to the patient. If I starting to change one function, it become a different compound. It will be a complete different regulatory process. So it is simply But good news is there is tons of people now in the world are starting to pick up this. They're making their own porphyrin with polymer, for example. They published in Nature Communication in the UC Davis group, Kit Lance group. They put a porphyrin with a polymer. They start to self-assemble into they call nanoporphyrin, right? So there is all these people are starting to working on porphyrin nanomedicine. I'm pretty happy because I want everyone to work on this. Even I went to a couple of years ago, I went to the Korean, the Porphyrin International Conference. I announced to the group, I bring about 10 talk with about 4 or 5 of my students to Korean, but nobody actually picked up on it. I was very disappointed. I thought everyone has all different porphyrin, they can work on this. But now I think they do.
Okay, very good. I don't see any more questions, so let's thank the speaker again.
Thank you.